and more salt.
But there's gonna come a
Eventually,
limit.
no more can dissolve in this amount of water. The quantity of salt dissolved in this solution, about 35 grams at room temperature, is a measure of sodium chloride's solubility in water.
35 grams of sodium chloride in 100 grams or 100 milliliters of water is probably what the solubility is. Can you see the sludge on the bottom? To me, that means that you've reached saturation and you just no more can go in. Okay. So these are generic terms. You know, we heard the 35 grams of sodium chloride per 100 milliliters of water at a particular temperature. That was the number of solubility. But if we say that a solute is soluble, we could say that a solute is moderately soluble, you know, like dissolves like. We could say that it's only slightly soluble or it's totally insoluble. Okay? Those are just kind of generic terms. So a little bit ago on the video, that person, who a woman, man, or whatever, that person, I guess it was woman, boys, had made a saturated solution. It means that when she or he tried to add more sodium chloride, there was just sludge at the bottom. I'm going to try to convince you, though, even though there's sludge at the bottom, it's what we call a dynamic process. Some of that sludge is dissolving, and some of the dissolved solute is precipitating out. Okay, so it's in what we call equilibrium. Okay. An unsaturated solution on the video we watched would be when they kept dumping more and more sodium chloride in. The solution was unsaturated. Okay? Early on in the process. Super saturated. I love super things. Anything that's super is kind of a tenuous sort of situation in physical science. Super means that it doesn't want to stay there. So a super saturated solution means that whatever reason, they were able to basically stuff more solute into that solvent than should be there. It's super saturated. But like this says, it's temporary and unstable. So here's some videos.
So super saturated, they figure out a way to dissolve more than there should have been?
Yep, exactly.
When nickel chloride is added to water, it dissolves readily.
I like that sound.
Because more nickel chloride could be dissolved in this solution,
Unsaturated.
the solution is called unsaturated.
All right. Next. Saturated.
When solutions of lead nitrate and potassium iodide are mixed, solid lead iodide precipitates from solution. The liquid remaining in the test tube is a saturated solution of lead iodide. Whenever a precipitation reaction occurs, the solution surrounding the precipitate is saturated with the product of the reaction.
So two clear solutions, okay, two clear made a cloudy. Now sometimes you may not buy this, but we're going to be talking more about precipitation reactions. If something turns cloudy, if you were to centrifuge it, you guys know what a centrifuge is? Okay, basically let gravity pull that solid down, you get like a solid sludge at the bottom. So kind of think of that when you see this. This would be a solid yellow sludge. Okay, so this is a saturated solution. Two clear solutions, when they mix together, made this saturated solution. An exchange reaction happened. We'll be talking more about this. This is supersaturated.
When supersaturated sodium acetate is poured onto a few grains of solid sodium acetate, the amount of sodium acetate dissolved in excess of the saturation point precipitates, forming a solid.
That's crazy.
That is cool. So
some of the liquid solution, which is now simply saturated, becomes trapped within the solid.
So that was clear. The stuff was like in unstable sort of situation. One way to get it out of its unstable situation is, and sometimes we do this in organic chemistry, we seed it, S-E-E-D, give it a seed. So put a crystal in there and voila, the stuff's like, dude, I didn't want to be in here anyway. So it starts precipitating out, getting to its normal saturation. So I think that's cool. So just kind of some still images. We looked at these, I think something like this on Wednesday. So the blue is the pure solvent, okay? And so here, B, you see, of course, the up arrows are dissolving, the down arrows are precipitating. So in B, notice we have more dissolving and less precipitating. If we and we'll be talking more about equilibrium, this is a physical equilibrium. At equilibrium, how would you say the rates of dissolving and precipitating are? They're equal, yeah, kind of showing you equal lengths. And so that's kind of what we have going on in a saturated solution. To me, if you have a sludge at the bottom, you kind of have this one right over here. Okay? All right. Another video. These are handy. This, again, is the sodium acetate we saw before, but it's very exothermic.
When a chemical hot pack is activated, the supersaturated sodium acetate it contains precipitates in a highly exothermic reaction. To reuse the cooled pack, we heat it to redissolve the sodium acetate.
So that little, can you kind of see that little, kind of looks like a nickel or something down there? It's kind of a flexible little thingy. I said that you can make a supersaturated solution come out of its supercondition by adding a seed. Another thing is just to kind of disturb it, and that's kind of what you do with that little, just kind of disturb it. And
So you could get one of those hand warmers and make it work again?
if it's this kind of hand warmer, yeah. Yep.
It's awesome. And all you have to do is just heat it up.
Heat it up. I've got some in the lab. We'll have to drag them out. So here's where I get to say, intuitively, like if you had sugar, well, if you've done much with candy, okay, made candy before on the stove, okay, if you want to get more sugar to dissolve, you heat it up, right? Mm-hmm. But not all things dissolve more when you heat them up. I'm going to try to kind of convince you of that. So solubility is a function of temperature. You can have more sugar dissolve in water at higher temperatures, less at lower temperatures, okay? But that's not always the case. So here we're going to kind of use kind of a chemical equation approach from left to right is how we proceed. So you start with the individual solid solute and liquid solvent on the left, and you're going to mix them, and what you're going to get is a solution on the product side. Well, what do the two-way arrows mean? It's an equilibrium, exactly. They're the same length. One goes from left to right, it dissolves. One goes from right back to left again, it precipitates out. This is actually showing you what that third beaker did a little bit ago, okay? So we have this process in equilibrium. And the solution is saturated above that sludge. That's how I think of it. Okay, so we're going to talk about the effect of changing temperature and what changing temperature affects, how that affects solubility. So if we heat something up, we're going to be adding, if we increase the temperature, we're going to be adding heat. And if we cool it down, we're going to be removing heat. That just makes sense. Here is a slide. You can see 1, 2, 3. There's 6 lines here. Each line represents a different substance. Okay. So along the y-axis is the solubility in grams of that particular salt per 100 grams of water. And then along the x-axis you have temperature. So just like our sugar, usually when you increase temperature, what happens to solubility? It goes up. Is there any on here that is not the case? As you increase temperature, solubility goes down. Which one? Yep. That guy? Yeah. So for lithium sulfate, as you increase the temperature, solubility goes down. We're going to actually kind of take a look behind the scenes of why that is. The other thing before I move on, this caption down here, okay, it's kind of nice. It talks about, it picks on potassium perchlorate. Get my, okay. It picks on those points there. At 50 degrees, can you see where region 2, would that be, if you had this much potassium perchlorate in 100 grams of water, would you be saturated or unsaturated? 2. Like if you're right here. If you've got,
Unsaturated?
yeah, you'd be unsaturated. Does that make sense? Yeah, you'd unsaturated here. What if you're right on the line?
You're saturated.
You're saturated. And then the caption here says, if you were to successfully be able to dissolve more potassium perchlorate in there than there should be in 100 milliliters, you would be supersaturated. That's kind of how that works. So ammonium chloride is one that kind of is the intuitive one, where at warmer temperatures it's more soluble. So all we have here is at room temperature, this test tube was prepared, and notice it's undersaturated. Okay, there's no sludge at the bottom of the ammonium chloride. And then when we lower the temperature, we remove heat, what happens?
It actually starts to crystallize.
It starts to crystallize, exactly. It starts to precipitate out. Yep. Okay. So this one, I think we might have watched this one before. This is just going to show the dissolving of potassium fluoride. And remember we said that if you're going to make any sort of solution, any sort of mixture, basically you have to break the bonds first of the potassium fluoride. Ionic bonds are pretty strong, and then you need to reform new bonds, kind of what we're going to call waters of hydration around each of the ions. So when bonds are formed, is energy released or energy required? What'd you say?
Bonds are formed,
When bonds are formed?
required. Released.
When bonds are broken, if energy is required. When bonds are formed, energy is released.
Oh,
Yep.
yeah,
So these waters of hydration around the ions, energy is released there. So it's kind of which one do you have more of, breaking, required, or forming, releasing? So enthalpies, delta H's. Which one, if it's exothermic, is it a negative or positive delta H? A 50-50 chance.
yeah.
Exo, right? Is it negative or positive?
Oh, yeah, that's
What?
negative.
It is negative.
It is?
Yeah. So you can see down here, and I know it's small, but it says enthalpies of hydration. Okay, exothermic, there it's negative. And to break the individual bonds for the potassium, the crystalline structure as it's solid, is negative, negative, which is positive.
Negative, negative.
Yeah, which is positive. So let's see what this video does.
The dissolution of potassium fluoride can be thought of in 2 steps, although the reaction does not really occur this way. First, we imagine the potassium and fluoride ions separating. This is an endothermic process. Then the ions are hydrated. This is an exothermic process. The combination of these 2 energies is the enthalpy of solution.
Makes sense. Okay. So let's see. Enthalpy of solution positive. So is it endothermic or exothermic? Positive plus 2 kilojoules per mole.
It's endothermic?
It's endothermic, yep. And, yep, very good. I'm going to follow up on that in a minute. Okay, so this is kind of a still image of the same thing. I looked and chased. In fact, I even posted I think I posted a website out there on their Twitter that actually instead of plus 2, this is plus 16. I can't explain it. So, same potassium fluoride. Switching gears from the salt potassium fluoride to sodium chloride, we could look at it the same way. You have to break those bonds between the Na pluses and the Cl minuses. That's going to require energy, positive delta H. And then when those new bonds are formed with waters of hydration around the ions, that's exothermic. Okay, and then your net energy required for kind of it's the enthalpy of solution, the dissolving process. That actually is where you add those 3 together. So, what's that?
Those kilojoules and moles of ions.
Yeah, yep. Yep, kilojoules per moles of ions. So these are some enthalpies of solution. No, these are some enthalpies of hydration. Formation of ions in aqueous solution. Okay. Now, Le Chatelier's principle, and I'm not French, so I'm totally butchering that, I'm sure, is an important thing that's going to come up in general chemistry too later on in the semester. We're going to take one look at it now. So this is an overarching principle in the way things work in our universe, Le Chatelier's principle. There are a lot of equilibrium. We talked about one equilibrium just this afternoon. One equilibrium was the whole, you take a solute and a solvent, it goes to form a solution. And then some of that solution precipitates back out, breaks back down into its solvent and solute. That's an equilibrium, that's kind of a physical equilibrium. So according to Le Chatelier's principle, you can have an equilibrium just ticking away, it's in dynamic, okay, and basically you stress that equilibrium, you poke at it, and that equilibrium is something's going to happen. If you want to add something to this slide, I was thinking, what'll happen is that your system will adjust and get back to I'm going to insert the word new equilibrium. I'm going to add that. It'll get back to an equilibrium where the rate in the forward direction is equal to the rate in the reverse direction, like those arrows kind of show. But it's going to be a new equilibrium, a new day. Okay? Why? Because the system was stressed. All right. Okay, so how do you stress a system? Well, you can monkey with the concentration of the reactants or products. You can go ahead and monkey with the temperature. You can go ahead and monkey with the pressure. These are all ways to poke a system that's in equilibrium. The one that we're going to look at with regard to the whole solvent, solute going to form solution is we're going to monkey with the temperature. We're going to monkey with heat, adding heat and removing heat. Okay. All right. Let's see, I guess I think so if you are gonna watch Le Chatelier's principle, it's a principle that just says you take a system that's in equilibrium and you stress it, okay? If you're going to stress it with heat, that's going to work really well as long as your process is either endothermic or exothermic. If it's releasing heat or absorbing heat, then you can monkey with it. It's exothermic or endothermic with regard to temperature. Okay, so here we go. I need to kind of break that out. I think what I'll do is kind of recreate what you're going to see here. All right. So I'm going to add solute plus solvent goes to form solution, and if it's saturated, some of that we have the precipitation occurring as well. That's the equilibrium. We're going to look at two scenarios, so I'll go ahead and write that again. The first scenario is going to be where this dissolving process is endothermic. So the delta H solution is positive. Right? We're good with that, endothermic. If that's the case, then I'm going to go ahead and I'm going to say it's endothermic. In other words, in order for it to proceed, it needs heat. It needs energy. Okay? Well, now this is kind of overarching thing of Le Chatelier's principle. It's kind of like, I think of it as like a tug of war. So Le Chatelet's principle says that if you stress the system, we are going to add more heat here. And I don't know how far this analogy works, but can you see where if we add more heat, we push it actually to favor, what we say favor this side. Okay, and this is the dissolved side. So if we add more heat, basically, temporarily, we're gonna go like this. And you get more dissolved. Okay? Add more heat, and I guess instead of pushing, you could say if you have more, and this is gonna work with us, this is gonna work for us later on with the Chatelet's principle. If you have extra stuff on the, what we call the reactant side, extra stuff on the left, it's gonna have to be used up, create more stuff on the right. That's kind of an overarching theme of Le Chatelet's principle, and it works here if we put heat as a reactant for endothermic processes. So this then is kind of, all except for the lithium sulfate, this was what we saw on all of those other, 5 salts on that table a little bit on that graph, okay? They must have been actually endothermic heats of solution. Lithium sulfate, I'm thinking exothermic. Kind of show you what that looks like. So it's kind of a push to that side. Okay. Then the other scenario is, well, I can't remember what I have next. Okay, so this is just kind of following up with our first scenario. If you have an endothermic process, you add heat, it's actually going to process in equilibrium. You add heat, and it's going to form more product. That's it. So the other scenario is exothermic. So I'm going to put down here for this second scenario, bless you, what you're going to see on the next slide is if it's exothermic, actually heat is considered what? A product. And our enthalpy of solution is going to be negative. Exothermic. Okay, so let's look at it now. If we add heat, and we kind of go with the pushing sort of thing, if you take it away, you pull. If you add it, you push. So if we add heat, can you see where, okay, it's going to do that sort of thing. Okay, and what is that sort of thing? Well, it's breaking back down into its components. In other words, it is precipitating. I'll put all these up here, so all these builds. So to me, yeah, this would be lithium sulfate. This would be Li2SO4. Because when we added more heat, we saw that it was less soluble. That's your Li2SO4. This kind of first look at Le Chatelet's principle. And then I think my next slide is just kind of analogous to what I had before. So the solubility of a solute will decrease with increasing temperature if the whole dissolving process is exothermic. Okay. So I hope you guys got this. Le Chatelet's principle is here to stay. It's kind of a make sense sort of thing. I don't know. All right. So if we lower heat, This, instead of pushing, has a pulling effect. So let me change my marker to blue up here. Let me go up here, and if I cool it down, remove heat, okay? If I remove heat, I'm not pushing, I'm actually pulling. So what do you think? If I remove heat, what's going to happen with regard? Am I going to get more into solution, or am I going to have a precipitate form?
Precipitate.
We're going to have a precipitate form. It's got a pulling effect, exactly. And here, if I remove heat, okay, I'm going to pull heat. I'm going to remove it. Okay, so am I going to have more into dissolved, or I'm going to have some precipitate out?
That way it's gonna dissolve more.
Yes, it's going to dissolve
fun.
more. Mm-hmm. Yep. So this kind of push if you add, pull if you remove. All right.
Inverse reactions are fun.
I don't know if it's really inverse, but it's, yeah. Okay, one last thing we need to talk about. I hope there's not a class after this one. I don't think there is, but. So have you ever gotten like a glass of water and you get it from the tap, you know, it's probably a little chilly, tap water is usually warmer than room temperature, and then you go to set, it sets out, and you come back a few hours later and you see the bubbles kind of forming on the side of the, okay. What happened is basically when you got it out of the cold tap water, it already had a certain amount of air or oxygen dissolved in it, okay? When you let it set, it got warmer, and what we're going to see is that gases are less soluble in warm temperatures. They're more soluble in cold temperatures. This has implications when you go to fish, I think. Okay. So that's all to say that if your solute is not a solid, but if your solute is a gas, and you're dissolving it in a liquid solvent, okay, the fact that it was, and to me I picture that in my mind because I've seen that so many times, you know, an old glass of water sitting around, you have bubbles of air, okay, so it's less soluble at warm temperatures, okay, so less soluble at warm temperatures. So that's actually our lithium sulfate, isn't it? Less soluble at warm temperatures. Okay, so this actually must be an exothermic process, and it is generally when your solute is a gas. So the addition of heat, like your cup of water sitting around, okay, will actually decrease the solubility of gas. If you cool it down, that will increase your solubility. So those little fishies, they maybe don't mind the cold water so bad. I don't know. More oxygen dissolved. So the next slide actually shows you the solubility of some gases, or a gas at different temperatures. Here we go. This is all for oxygen. Notice we have warming temperatures, okay? And what's happening to the solubility as the temperatures are increasing?
Going down.
Decreasing, yeah, solubility decreases. Sigh, assignment slide. Let's take a quick look. 1339. So yeah, you guys should go home and try to improve on your slushy making and let me know.
Did you click that already?
What's that?
Did you click that already?
I did. I'll take yours. Any other homework? So this one, the first one, even the second one, you're supposed to be referring to this figure that we looked at before. First one's looking at ammonium chloride. And thank you. You're supposed to come up with the molality in a saturated aqueous solution at 40 degrees. So you find 40 degrees on there. I don't know why I've got like 45 degrees, but you find 40 degrees on there, see where your ammonium chloride, intersects. Doesn't look like I picked 45 instead of 40. So don't do what I wrote, do what you think you should do. And you're gonna pick off that number and,
That's grams.
Are you
yeah.
serious? Okay, I did do 40. So I picked 40 and then I go and it's about 45 grams. So you're gonna have to do your magic with turning that grams of ammonium chloride per 100 grams of water into molality, which won't be too bad because molality, yeah.
Mix of NH4s,
Yeah, molality requires kilogram of salt, which is H2 on the bottom, so that's not too bad. Okay, the next one, you're turning attention to the potassium perchlorate, which we picked on before with the 1S and 2. Estimate the temperature at which a saturated aqueous solution is 0.200 molar. So, what did I do? I think you need to, let's see what my hints are. Yeah, you need to convert that molality to grams of solute per 100 grams of water, and then pick it off of there. Yeah. Next one, potassium perchlorate again. It gives you the mass, the water mass of the potassium perchlorate, and you're supposed to say, based upon those masses, is it going to be, where's it going to fall? Saturated, or it's going to be unsaturated or supersaturated? The last one? Well, that was the last one. There's 3, and I did 2 on the first one. Okay. So have a good weekend, everybody.